Welcome to Adventures in Mathematics. I'm your host, Alan Carlisle, and today we're going to hunt for the elusive constant that the integral that you see on the slide, what it converges to. Over the entire x-axis, in other words, from a negative infinity to a positive infinity, of the function e to the negative x squared dx. And of course, e is our Euler number, approximately 2.718. And even though this is an improper integral, we cannot use the traditional methods of taking the antiderivative and employing the fundamental theorem of calculus, simply because the antiderivative of e to the negative x squared is not a simple function or combination of functions that we're familiar with. So we're going to have to use some mathematical tricks and employ some methods that will take us down some very interesting avenues. So let's take an adventure and discover the amazing constant that this particular integral converges to. Okay, this is a graph of our function e to the negative x squared, and it looks kind of familiar, doesn't it? Matter of fact, that's what it is. It is the bell curve, otherwise known as the normal curve in statistics. And notice that it starts up here at the apex, or the maximum, is at y equal 1. And as we proceed to the right, it gradually goes closer and closer to the x-axis, which means it approaches 0. And the x-axis is indeed an asymptote. On the negative side, it does the same thing. The reason for this is because our function is symmetric about the y-axis. So what we're looking for is the area under this curve across the entire x-axis, and the area is equal to a very interesting constant. That's what we're looking for. Okay, now what we have here is a representation of our integral in two different variables. The first integral that I'm circling here is the one that I presented at the beginning. This is exactly the same integral. The only difference is we have a different variable, y. In this particular integral, we're integrating across the x-axis. And in this particular integral, we're integrating across the y-axis. But since y and x are simply dummy variables, both converge to our elusive, mysterious number, c, our constant that we're looking for. Now, if we multiply these two integrals together, which is what we're going to do, we're going to use a little mathematics finagling or trick, and we'll get c squared, the square of our constant, multiplying the two integrals together. And it turns out that we can express this product in the form of a double integral in the xy plane. The double integral over the region R, which happens to be the entire xy plane, of e to the negative x squared times e to the negative y squared dA, where dA is simply the product of our two increments of dx times dy, giving us our increment of area dA in the xy plane. When we do that, we can employ our addition rule for multiplying numbers of the same base. Adding a negative x squared to negative y squared, we get our new function in two variables, x and y. So here we have a double integral of a multi-valued function over the entire xy plane, the region R. This is the trick that we will use to get our integral into something that we can manage. And what you see here is a 3D rendering of our surface. The function in two variables, x and y, e to the negative x squared plus y squared. Notice that this also represents a surface of revolution. If you take and revolve the normal curve about the z-axis, this is what you'll get. So what we're looking for now in multiplying the two integrals together is the volume bounded by this sheet that you see in the xy plane. Okay, this is our double integral over the region R, which again is the entire xy plane, of e to the negative x squared plus y squared dx times dy. The volume under the 3D graph that we just looked at. Now what we're going to do, the trick that we're going to perform, is to put x and y into polar coordinates. Something very nice happens when we do this. But let's review quickly here. In polar coordinates, x is equal to r cosine theta, r the radius, theta is the angle, y is equal to r sine theta. When we make our substitutions for x squared and y squared, we will substitute r squared cosine squared theta for x squared, r squared sine squared theta for y squared. When we do, we make our substitution for x squared plus y squared, factor out the r squared, use the fact that cosine squared theta plus sine squared theta equals 1, and everywhere we see x squared plus y squared, this will be substituted with r squared. Simplifies things quite a bit, doesn't it? Okay, so what we have, after making a replacement of the variables for x squared plus y squared, here we replace r squared, and for dx dy we replace dr d theta. But notice this little factor here. What in the world does that mean? We have to remember when we make a change of variables like this to introduce what's called a Jacobian. Okay, a Jacobian is nothing more than a determinant that is represented by partial derivatives dx by dr, dx by d theta, dy by dr, dy by d theta, and of course must be a factor of any multi-valued function when you have a change of variables. Now, this is a determinant. So when you take the derivatives, dx by dr becomes cosine theta, dx by d theta becomes negative r sine theta, dy by dr. Now the partial derivatives, of course, is sine theta, and the partial of y with respect to theta is r cosine theta. You can check this out on your own. It's a very simple determinant. When you evaluate this determinant, you get the very important result of r cosine squared theta plus r sine squared theta, factoring out the r. And of course, here we have our trigonometric identity, which equals 1. Cosine squared theta plus sine squared theta equals 1. So our resulting Jacobian for this particular change of variables is simply the radius. Alright, now to finish this lesson, we make our substitutions for x and y and get the double integral in terms of the radius r, angle theta at polar coordinates. And when we do, we get the following double integral integrated over the entire xy axis, meaning that the inner integral in terms of r is evaluated from 0 to infinity, as r, in other words, as the radius goes from 0 to infinity, and theta goes from 0 to 2 pi. Notice that the function r times e to the negative r squared is a manageable function, one that you should have seen many times before as a calculus student. And evaluating this integral simply involves letting u equal r squared, making our substitution in the integral, then gives us du equal to 2r dr. Substituting that in the inner integral gives us, in terms of our new variable u, 1/2 evaluated from 0 to infinity. Again, you will go from 0 to infinity when you make the change of variables. E to the negative u du, which is a very simple antiderivative, which is itself taking the limit using the fundamental theorem of integral calculus as u approaches infinity. E to the negative u approaches 0. Of course, e to the 0 itself is 1, so this inside the parentheses evaluates to 1. So we get negative 1/2 times negative 1 is a positive 1/2. Now that's the value of the inner integral. Therefore, the resulting integral, evaluating the outer integral in terms of theta, gives us the 1/2 we just found, evaluated from 0 to 2 pi of d theta. And it's very simple. You can do this substitution yourself. The value of the integral is 2 pi. And when you multiply 1/2 times 2 pi, you get pi. This is the value of c squared. C squared is pi. Therefore, the constant that we've been looking for this entire lesson is, surprise, surprise, the square root of pi.